Machine learning for finding programming defects and anomalies. Looks very interesting. Go ahead.
Okay. Guten Tag.
Guten Tag.
Ich spreche nur ein bisschen Deutsch. So I will speak in English instead. We're going to talk about using machine learning to find bugs in programs. I'm very glad to be here. So here's my agenda. I'll talk a little bit about static analysis. I'll talk about how it can be used for API misuse. I will talk a little bit about how we know what normal usage of APIs is. Then I've got some slides on how static analyzers can find anomalies, having learned what normal is. And then I've got some caveats and conclusions. So static analysis. So static analysis is any technique that computes a property of your code without actually executing your code. So you're all familiar with dynamic analysis, which is its counterpart. With dynamic analysis, the key thing is that you're executing the code against real data, whether it be unit test data or integration test cases. And you're computing some property. Maybe you're computing correctness, or you're looking for coverage, or you're looking for performance information. That's dynamic analysis. You're running against real data. The key thing about static analysis is because you're not running the code, you're not executing it, you don't need test cases. The results are, in principle, consequently good for all possible executions of the program. Or it's actually fairer to say they're good for all possible inputs. So static analysis is usually this two-phase process. First of all, you extract the information from the code by parsing it. And that creates a set of intermediate representations like control flow graphs, abstract syntax trees, exactly the kinds of things that are used by a compiler, except that in static analysis, what we're doing with that information is looking for problems, looking for bugs, anomalies, defects, and so on. So static analysis has been run for a very long time, of course. In the early days of static analysis, it was designed to do stronger type checking. So you're probably all familiar with the lint family of languages. Sorry, the lint family of tools. The original lint was written 35, 40 years ago, and it was to do better type checking of C programs because the designers of C concluded that the compilers were far too weak, and you needed this extra checking in order to be able to write code that was correct. Static analysis these days is also used for checking performance for coding guidelines like Misuse C, Misuse C++, and some maybe security guidelines like the Cert Secure coding standards. You can also use it for architecture analysis, computing things like cohesion and coupling, and whether your architecture is followed by the code. That is, whether the code conforms to the architectural requirements. And of course, metrics is another thing. I think Roy mentioned that this morning. All this is static analysis, but these days, when people say static analysis of code, usually what they mean is finding bugs. Now, CodeSonar does some of all of these things, but its primary purpose is for finding bugs. Now, CodeSonar is a bug hunter. It is not a verifier. If you go fishing in the lake for some fish, you don't expect to catch every fish in the lake. So CodeSonar is a little bit like that. It's fishing for bugs, but it's not guaranteeing to find all possible bugs. There are other tools that do that, but CodeSonar is not one of them. For many of the programs, especially in C and C++, because it's such a badly defined language, it's impossible to do so for most programs and most properties. So it's a bug hunter. Now, static analysis or the kind of tool that I'm talking about here, can find bugs in, roughly speaking, 3 categories. So the first category is the most important category for C and C++. This is undefined behavior. So undefined behavior, and there's lots and lots of undefined behavior in C. If you look at the standard for C and C++, there are pages and pages and pages that describe undefined behavior. And the problem with undefined behavior is when you hit it, anything can happen. Your computer can catch fire. According to the standards, that is a legal thing to happen. It doesn't ever happen, of course, but what the compilers do as a consequence is to, and this is the only thing that it's sensible to do, is to assume that the undefined behavior cannot happen. But in practice, what happens is the program can either crash right away, or worse, if you're lucky it crashes right away. A worse thing is that it silently corrupts some data, and subsequently, sometime later, it will maybe do the wrong thing or crash then. If it crashes immediately, you're lucky because you know you have a problem. If it doesn't crash immediately, then it's very difficult to trace that information back to the point where the bug occurred. Undefined behavior includes things like using uninitialized variables, null pointer dereferences, or indeed any reference to any address that is illegal. Buffer overruns, of course, and then even concurrency things like data races. The second category is misuse of APIs. Now, you all use APIs, whether it be the C library, or STL, or the operating system libraries, or a crypto library like OpenSSL or something like that, or a windowing system library like Qt and so on. Those APIs are ubiquitous, and they all have rules. And what happens if you break the rules? Well, who knows? Usually that kind of stuff isn't very well defined by the API itself. Sometimes you get an exception, sometimes you get a crash. Again, you might be straying into undefined behavior by breaking the rules, but you don't really know. So, the consequences of the misuse of API can be just as bad as the previous one, but we think of them in a different category. So a good example of this is if you close a file descriptor twice, that's illegal. So it's, the consequences are going to be dependent on the particular implementation of the C library that you have, but it's definitely a bug. Another good example of the API misuse is if your program is allocating and deallocating finite resources like memory or file descriptors or graphics handles and things like that. There's a protocol for dealing with those. You allocate, you do something with it, and then you free it. And that can be malloc free, or it can be open close with file descriptors and so on. A memory leak, or any kind of resource leak, is in that same category. This afternoon I'll show you some examples of these in real life. The third category is code that is unlikely to cause your program to crash, but looks suspicious in some way. And a good example of that is dead code or redundant code. So if you get an if condition, and the condition is either always true or always false, then there's something not right about that, potentially. Now sometimes these things are completely deliberate, sometimes they're actually useful, but a lot of the time, if you don't know that you have it, then it's, they can indicate bugs. They often correlate well with the fact that the programmer didn't understand something important about the code. And furthermore, there are some coding standards that completely forbid things like redundant code or dead code or that. Many of the checkers that are violations of coding standards, like MISRA and so on, are in that third category. Now, as well as that, you can write your own checks. So if there's some domain-specific invariant of your code, and you want to know when your programmers are violating that invariant, you can code it up. This can be as easy as changing a config file parameter. If the property that you want to check is very similar to a property that we already check, then we've often anticipated the ways in which you might want to configure it and have exposed parameters through the config file that will allow you to do that. Or you can get into the API and you can change the, you can get into the API and you can write code that will access the underlying program model, and that includes the things I mentioned earlier, the abstract syntax trees, the control flow graphs, the call graphs, and so on. And if you're using CodeCenter and you're not doing custom checks, then it's really, really worthwhile to look to see if you can take advantage of those, because you can vastly increase the value you get from the tool by doing that. So now what I'm going to talk about today, though, is using machine learning to strengthen that second category, the API use category. So let's talk about that a little bit first. So what are the kinds of things that can go wrong when you're using an API and break the rules? So you can pass in parameters that are out of range or that are invalid in some way. So some APIs require, if it's a pointer, it must always be a pointer to a malloc region, or some other APIs expect a pointer to a static string. And if you violate that, then that's a problem. So bad parameters, resource mismanagement, like I mentioned earlier, leaks, double frees, use after free, and so on. And that goes not just for memory regions, but for the other kinds of resources that you might manage, like file descriptors and so on. Then there are type state properties. So this is where each instance of a given type must go through a sequence of states in order for it to be valid to use. A good example of that is the socket API. So with the socket, you do an open, then there's a bind, then there's a connect, and or something like that. I can never remember the exact sequence, but there's a sequence of steps you must go through for each socket before it's valid to read or write to it. Then race conditions can be caused by API misuse as well. But what I'm going to talk about today is mostly the ignored return value checker. So this is you're calling a function, you're getting a return value back in the return code, and it's being ignored. Now it may not be ignored immediately, it may be assigned to a variable, and then that use of that variable is subsequently ignored. And that turns out to be a fairly important check. It's already in CodeCenter, but what we're going to be doing today is talking about how you can use machine learning to enhance it significantly. So the key thing about program analysis is there is normal usage and abnormal usage. So for example, with ignored return value, if you look at that first example, there's call and malloc, and the return value is being thrown away. The programmer hasn't even attempted to save it to a variable. So it is never right to ignore that return value. If you ignore it, then you've leaked memory immediately. And if you ignore it, then you don't know whether the malloc even succeeded or failed. So it's always wrong to do that. It is very rarely right to open a file descriptor and then not use it. There are some use cases where it's fine, but they're kind of rare. And similarly, if you call open and you assign it to a file pointer, and then you never use that pointer, or that's actually a file descriptor, it should be FD rather than FP, then if you never use that and then you do another open and write over that value, then you've effectively ignored the value that you got from it the first time as well. So it's wrong to do that as well. Now, here, these functions, malloc and open, are very widely used. They're used in almost all C programs, and indirectly in C++ programs as well, because malloc is just like new. So static analysis tools because they know what these functions are supposed to do, they have built in to them that knowledge, and they can have checks that that exploit that knowledge to find problems. So now we've written those specifications for hundreds and hundreds of functions. And that's great. It means that when you use a static analysis tool that, like Codestar, that has models for those functions, you get the benefit of them. But there are lots of APIs, dozens and dozens that are in wide use, and that means thousands and thousands of functions for which we have not written these models. So the key thing is, normal behavior can be written by hand by tool vendors, and that's what we do. But there's so many things for which you would want to know what normal behavior is that you can't do it by hand. There are just too many things. Consequently, that's where we turn to machine learning. So the key point here is at the top. Most code is right most of the time.
Yes.
If it's not right most of the time, then the code is going to just fail immediately. But what I mean is most code that's at least somewhat mature. And because most code is right most of the time, anomalies, that is things that are unusual in the code, correlate quite well with real defects. So, for example, if this was your code, then you find some anomalies in there, and they could turn out to be real bugs. But even non-buggy anomalies, like this down here, I've got a dog among these butterflies. Even non-buggy anomalies, that is anomalies that are deliberate and are not bugs at all, it's often very useful to know about those as well, so that you can, well, first of all, document them to indicate that yes, it's unusual, but this is deliberate. Or to take special measures to maybe test them a little bit more thoroughly, because things that are anomalous generally don't get tested as well as things that are normal. So the key thing is, how do you learn what normal behavior is? So imagine you've got some code that looks like this. You've got this function xWrite, and let's assume that the analysis has no prior knowledge whatsoever of xWrite. It's some function in some API that's being called, and the analysis doesn't know what it's supposed to do, so it doesn't know what normal is. So by looking at the code and just observing the places where xWrite is being used, well, in all of these, what do you notice? The return value is being assigned to something. And so that tells you that it is normal for that to be the case. So if you have at least some baseline number of samples in your program, and you notice that the return value is used in almost all of those, then places where you don't use the return value are anomalies. So if you see something like this, you think, this isn't like the other things. Maybe there's something wrong here. So, the bugs I'm going to show you are bugs that we found in open source software, and I believe that we reported most of these, if not all of them, to the authors, and they confirmed that yes, it was a bug, and yes, they needed to fix them. So here's one that was definitely confirmed. So you've got this called a G-stir escape here, and so its parameter is this param stir, and the second parameter is null. And subsequently, you've got this stir concat, and what that is clearly doing is making an SQL statement by concatenating together lots of strings.
And just by glancing at this, it's clear that what's happening here is that there's this parameter that's coming in, and the programmer wanted to escape special characters so that they were safe to pass to the SQL statement construction. Now, if you read the manual for that function, gstir-escape, what you notice is this. It returns something. It returns a newly allocated copy of source, where source is the first parameter there, with certain characters escaped. So what it returns is something new, but notice that the return value here is being entirely ignored. So this is two bad things. So first of all, the ignored return value, because this is a newly allocated copy, it's being allocated with malloc. Because you've ignored the return value, you've instantly got a leak of information. Well, a leak of memory, rather. But it's actually slightly worse than that, because you pass in parameter here. Now this function doesn't change what's in that string. So what's being passed in here is an unescaped value. And passing in unescaped values to something like this means that you're going to end up with a SQL statement that is potentially badly formed. And that is exactly the kind of thing that leads to an SQL injection vulnerability. Okay, so that was a nice one. Here's another one. This one is a little bit more complicated. So we're saying ignore return value for this variable called URI, and I've highlighted where URI is here, so it's declared up there, so it's a local variable. It's assigned to there, and it's also assigned to there, and it's actually used down here. So you might think, well, I am using the value of gfile get URI. You're assigning it to that variable. But the codes on our analysis, it's not just looking to whether you're assigning the variable to something, it's whether you're using the value that was assigned to the variable. So sure, the value is being used on here, but what it's saying is that there's a path through this function where you hit this go to out, where you're not using it, where its use is being skipped entirely. And so this unusual condition is causing its value not to be used. So consequently, the call to that function is completely useless. Now again, if that had been, I can't tell from this, if gfile get URI was something in allocated memory, you would have also ended up with a memory leak. That was a confirmed bug as well. Now, so far I've just been talking about ignored return values, but there are lots of other things that you could ask about APIs. And here are some of them. So when you're using an API, you're passing in some values. Are those values in the right range? Upper bounds, lower bounds? What are the properties of the pointer, if it's a pointer valued thing? Is it a dynamically allocated pointer? Is it allowed to be a static pointer? And so on. Is it a pointer to a null-terminated string? Does it have to be, say, a pointer to a file descriptor? And so on. So there are all these other kinds of properties that you might want to check for. So just to give you a flavor, here's another bug that we found. So notice we've got this string here, char stir. It's a constant length string. Strlen is a macro. And but notice that it's being declared without it's being initialized, which is fine. But down here it's being used. So you've got this get time of day, and if that fails, then you call this fprintf. So this is an error condition. But what's happening here is really weird because it's fprintf takes a file descriptor, in this case std, and the next thing is supposed to be a format string. That parameter is expected to be the thing that contains the percents and so on. But it's not, because clearly the programmer was confused here, because the thing that contains the percent directives is the next parameter. But we find this because, first of all, it's slightly anomalous to have this be a variable. In most cases, it's a constant string. And furthermore, it's extremely anomalous to pass in something in that parameter which is known to be uninitialized. So the consequence of this is probably going to be some kind of, well, what will be written standard there is some garbage data. Because this is uninitialized, you don't know what you're going to get. In fact, you do know what you're going to get up to a point. What you'll get is what's on the stack. So what was on the stack when the function ran, and who knows what that's going to be. But in any case, it's wrong. Now, this particular bug, it turns out that it's actually fairly unlikely to be triggered, because it's quite rare for get time of day to fail. And this is clearly something that is only executed at get time of day fails. But somebody wrote this, so there's clearly an expectation that it might fail. And in such case, well, surely the code that is expected to handle that failure should work. But clearly there's a bug. And this also illustrates that the kinds of bugs that static analysis is really good at finding are those which occur along rarely executed paths of code. So probably this code was tested thoroughly, maybe, but it's really, really difficult to test code that checks every error path. So that's probably why this lasted so long. I don't think this was an especially safety critical application. Here's another one. So let's see. So the key thing in this one is you've got this function, RTBG trim. It takes a string as input. And I've elided some of the code here that's not especially relevant, but you can see that there's a definite path through this code where what's being returned is exactly what was passed in as a parameter. And notice that on other paths through the code, it's either returning null, or it's returning something which is given back by a call to palloc. Now palloc just happens to be a wrapper to malloc. So this is, just by observation, this is really poorly designed function, because whatever gets returned should be consistent. So if it sometimes returns something that is on the heap, and sometimes it returns something which is not also on the heap, then you don't know what to do with the return value as a client of this function. Sometimes you're allowed to free it, and sometimes you're not. It's really, really bad design. And then, and as a consequence of that, here's a call to getenv. The getenv is putting its value in this variable here, which is being passed to RTPG trim, which is the function that we have here. So whatever came back from getenv, and that's not on the heap, is in some cases passed to pfree. So you've got this, so env is what comes back here, and so pfree is being passed something that was definitely not on the heap. And this turns out to have caused a crash in this program if it was set up to execute that path. Now, you may be wondering, well, things can be anomalous, but they're not necessarily wrong. And there are a few other weaknesses of this approach. So, full disclosure, here are some of the caveats. So first of all, anomalous does not mean buggy. Often it correlates really well with buggy, but it does not mean buggy all the time. And furthermore, machine learning, as used in this context, can also learn bad behavior. So if there are enough instances of bad code out there, then there's a potential that it will flag good code, because it's not the same as the commonly occurring bad code as a bug. So our experience is that that's fairly rare. But here's an example. So having done this analysis, we've noticed that G-type register static simple, a value of 0 in that position is very anomalous. That occurred very, very rarely in the corpus. But furthermore, this value, G-type box, which is a macro that expands to some constant, is also anomalous. And as it turns out, that this code is not buggy, it's just unusual. And in fact, what this tells us is that for this analysis to work very well, it's not a good idea to look at just one anomaly at a time. The fact that this is anomalous and that is anomalous actually weakens the case for it to be a bug. So if you've got one anomaly, then yeah. If you've got two anomalies, then you think, well, maybe it's different because it's just unusual. And furthermore, normal may be bad. So I've had this conversation with my children multiple times. Peer pressure is very strong. So you often exaggerate and say, well, if everybody jumped off the cliff, would you do too? And of course their answer is, well, of course not, I'm not that stupid. But a computer that's doing machine learning saying, well, jumping off the cliff, if everybody does it, then it's the completely normal thing to do, so I'm going to do it. So yes, it's true that normal may be bad. And my last example is a good illustration of that. So, and this is actually a fairly famous bug in a fairly simple problem. So this is the binary search algorithm. So you've got an array here of integers. You've got a value that you're looking for. So imagine your array is sorted, and you want to find a point into which you should place that value if it doesn't already exist in the array. So it's binary split search. You basically pare down the upper bound to the lower bound of the array until you find where the problem is, or not where the problem is, where the point is. This is the classic implementation of this algorithm. You will find this algorithm exactly as it is in many textbooks. The problem is, it has a bug in it. Anybody know what the bug is?
No.
Now, it's not a bug that is likely to occur very often. Anybody want to try? I've got a prize for whoever finds the bug.
What?
Huruvida elfok never little than you.
No, I think that's okay. Okay, I'll just tell you. So there's potential overflow here. So if you take two integer values and add them together, then that can overflow, right? If they're sufficiently large, that can overflow the number of bits that are available for an integer value expression in C. So by adding two very, very large numbers together and dividing by 2, you're ending up with something that isn't right necessarily. So what you should have done is to take L, take the difference between the upper bound and the lower bound, and divide that by 2 and add that to L. So that's guaranteed not to overflow, whereas that does have the overflow risk. And so if you turn this machine learning thing loose on lots and lots of code, I'm not sure this is even the kind of thing that would be learned by it, because we're focusing on functions. But this is a good illustration of how bad code can spread and be thought of as normal. So I wouldn't be surprised if there were similar things having to do with API usage that are just wrong, but which have spread through the code bases and are thought of as normal. So, the conclusion is that machine learning can learn bad habits as well as it can learn good habits. Okay, so this is my last slide. Here are my conclusions before I can take some questions. So the key thing is static analysis, good for finding bugs. I hope it persuaded you of that. If you're not persuaded, then this afternoon I hope to persuade you really. Not just violations of coding style, but stuff that's a lot more significant and serious than coding style violations. Anomalies in code correlate quite well in our experience with real defects. But again, knowing what normal behavior is tricky. And so using machine learning in very large quantities of code can help the analysis find real bugs because it can figure out what normal is by looking at lots of things. This can work at many scales. So you can do machine learning on just the one program that you're analyzing. You can do it in all the code that's in your institution, or you can reach out and do it in lots and lots of with lots and lots of other programs like open source programs and so on. And with that, I will take questions.